All right, so we're going to talk about acceleration now. So let's officially define this. So acceleration is the rate of change in velocity. And we'll make sure that we emphasize that it's velocity. So rate of change of velocity. And so acceleration is denoted by a little a. And a is equal to delta v. And if you remember from chemistry, the delta means change. And so change in velocity over time. Anytime you do something divided by time, that is your rate. So rate is just something divided by time. Divided by time. So another way you can write this, to find the change, you would take the final minus the initial. And so this equation and this equation are identical. Change in velocity over time, change in velocity over time. Now your units are a little bit different because you have meters per second, which is your v. So meters per second is v per second, which is your divided by time. So acceleration has two time components. So either two components. So either 2 seconds, hours in seconds, year in seconds, but there has to be two time components. Another way you can write this would be meters per second squared, because seconds times seconds is not 2s, it's s squared. So meters per second squared. So acceleration, because it's dealing with velocity, acceleration is also a vector quantity, which means it has magnitude and direction. Here specifically for acceleration, acceleration will always have a direction that is expressed with the sign. So positive acceleration means an increase in velocity, and a negative acceleration is a decrease in velocity. The term you've probably heard a lot is decelerating. Acceleration, by definition in physics, is either positive or negative acceleration. Deceleration is a term we use specifically for this decrease in acceleration. We can also see acceleration whenever we change direction. So it goes back to that question from speed and velocity. If you're going around in a circle at a constant speed, are you going at constant velocity? And the answer was no, because you are changing direction. We'll talk about this one when we get to circular motion. So for right now, don't worry about it, but just realize we're going to revisit it in circular motion. So let's do some quick examples. Just these are more concept than actual math problems. So we said that acceleration is the change in velocity over time. And so our change in velocity, we went from 50 to 75. So 75 is our final, 50 is our initial. So there's our change in velocity, and this happens in 10 seconds. Sorry, 10 seconds. And so we have 25 over 10, which gives us 2.5. Now here's where the units are fun. These are measured in kilometers per hour, and then time is measured in seconds. So here's one of those where it's kind of strange, where it's not seconds and seconds, it's hours and seconds. But this is a perfectly acceptable acceleration unit because there are two time components, hour and seconds. Hint, this is a question on WebAssign. So you are traveling at a constant velocity of 75 kilometers per hour. What is your acceleration? Well, if you're going at constant velocity, your initial is going to be 75. And your final is going to be 75. Is there a change in velocity? No. No change in velocity. So if we do not have a change in velocity, then time that we've got, as long as we're going constant velocity, 0 divided by any number. So it's still going to be an acceleration of 0. So if you are going constant velocity, your acceleration is 0. So now, the big four. The Big Four is a set of equations that you can use for any acceleration problem. You're going to use them in acceleration, you're going to use them in gravity, you're going to use them in 2D. They are going to be your best friends. So the first thing is an assumption. We assume acceleration is constant. That way we can plug in a number, a single number for A. It's either going to be 0, which is that constant velocity situation, or it's going to be some non-zero value, so 1, 2, 3, 4, 5, 100, a million, whatever. Other variables that are going to be very important are listed right here. A is acceleration, V naught is initial velocity. The little 0 means a time of 0. Then we have just V. The reason why we use just V is because it can either be your final velocity in the situation or your velocity at any instant. It depends on what you're looking for. So it's just V. D is displacement because, again, all of these are vector quantities: acceleration, velocity, displacement. They all have to be vectors. And, of course, T is time. So here are the Big Four. Get to know these. You do not need to memorize them. You will always be given an equation sheet for tests. But you need to know how to use all 4 of these. You need to know what situations to use these for. Now let's talk about how we're going to solve these equations before we actually start using these. We solve them using something we call the guess method. And so the guess method is where you go in order. You write your givens. This is what you are given in the problem. You determine your unknowns. This is what you're looking for. Then from those two, you choose your equation out of those Big Four. You substitute in your givens, and then you solve for the unknown. So whenever you're asking us questions on how to do this, we're going to make you go step by step through this. So get used to it. You need to show your work. So example 1, it says a bus traveling at 30 meters per second accelerates at a constant 3.5 meters per second squared for 6.8 seconds. What is its final velocity? So the reason why I did the underlining is because honestly it helps to know where your numbers are. Once you have them underlined, you can then label your givens, which is step 1 in the guess method. So it says a bus traveling at 30 meters per second accelerates. So that means it was initially going 30 and then it decided to speed up. So this is going to be our initial velocity. It accelerates at a constant 3.5 meters per second squared. So notice 2 time components. It also says it accelerates at this rate. So this is our acceleration, our A. And then 6.8 seconds is, of course, our T. We're looking for what is its final velocity. So that's just going to be V. So looking at our 4 variables, there is one equation that has those 4 variables: V, T, A, and V naught. The equation that has these 4, V equals V naught plus AT. There's your equation. Then you substitute in what you know. We know, this is our unknown, we know V naught is 30 plus acceleration, which is 3.5, times our time, which is 6.8. So the next step is to multiply 3.5 times 6.8. So we get 30 plus 23.8. And then lastly, we're going to add those together, and we get 53.8. And our unit is meters per second. Second example. Now, don't get confused where it says constant rate. It's still accelerating. It doesn't say constant velocity. It says accelerating at a constant rate. That just means that A is constant. We assume that. So we're going from 15 to 25. So this is our V naught, and this is our V. While it travels 125 meters, that's our D. So there's our givens. Then it says, how long does this motion take? We're looking for time. Again, there's one equation that has those 4 variables. V equals 1/2 V plus V naught times T. So we have 125 equals 1/2 of v, 25, plus 15 times t. 25 plus 15 is 40. And so half of 40 is 20. So from here, you're just going to divide by 20, and you get a final t of 6.25 seconds. All right, our third example. A pilot stops a plane in 484 meters using a constant acceleration of negative 8.0 meters per second squared. How fast was the plane moving before braking began? So first of all, here we have a negative acceleration. So that's our A. The negative just means we're slowing down, which is what it says here. 484 is your D, because it's in meters. But we need one more given. You always need 3 givens in an acceleration problem. Well, it says right here that the plane stops. So if it stops, what is its V? 0. So our final velocity is 0 because we are stopping the plane. So you're going to have to read into this sometimes to find that last given. So then we're looking for how fast was it going when it began. So we're looking for V naught. Again, there's only one equation that has those 4 variables. So V squared equals V naught squared plus 2AD. And so we have our 0. We're looking for V naught plus 2 times negative 8 times 484. So we have 0 equals V naught squared minus 7744. So all I did was multiply those 3 numbers together to get 7744. So now we're going to get V naught squared by itself. If we subtract this, then we're going to add it to this side. And so we get, I'm just going to move over here, V naught squared equals 7744. And then from there, in order to undo the square root it. And so then your V naught is going to be 88 meters per second. So it started at 88 meters per second, and then it went to 0. All right, last example. Starting from rest, a race car moves 100 meters in the first 5 seconds. What is the acceleration? All right, well, first, let's underline our numbers, and let's label those. That's a D, because it's in meters, and that's a T, because it's in seconds. Well, I said we needed 3 knowns for any acceleration problem. Here it is. Starting from rest. So we're starting at 0. So our V naught is 0. Not our V naught, starting. And then we're looking for A. Again, there's only one equation that has those 4 variables. So, yeah. And so we have 100 equals V naught, which is 0 times 5, plus 1/2 A times 5 squared. Now notice only the T is squared. If A and 1/2 are also squared, this will all be in parentheses. Since there are no parentheses, only T is squared. So we get 100 equals, that's 0, so it drops out. 1/2 of A times 25. And then, let's see, half of 25 is 12.5 times A. And then we're going to divide by 12.5, both sides. And so our A, finally, is 8 meters per second squared.